Today, we're tackling a massive question. How does an AI actually understand language? I mean, really get it. We're going to get right to the heart of the AI revolution by breaking down the one piece of tech that made it all possible, the transformer.
I mean, if you've ever played around with something like ChatGPT, you know that feeling, right? That sense of awe. But have you ever stopped and thought, wait a second, what is actually going on inside the machine when I type something and it writes back a perfect response?
Well, that's exactly what we're going to unpack. And let me tell you, it is not magic, not even close. It's really a story about human ingenuity, a whole series of brilliant solutions to some incredibly tough problems, one building on top of the next.
All right, so where does this story even begin? Well, it starts with the most basic problem you can imagine. See, a computer has no idea what cat or happy means. It only speaks one language, the language of numbers. So the very first challenge is, how do you translate our words into its math?
Okay, that first step is something called tokenization. It sounds fancy, but all it really means is you take a sentence and just chop it up into smaller, manageable pieces. We call these tokens. They can be whole words, sometimes just parts of words, whatever works. This is basically step one in teaching a machine how to read. Now, once you have these tokens, you've got to give them some meaning, right? The old way of doing this was, well, it was super clumsy. Every single word was its own separate thing. Bear and bears, totally different. But the new way, using what we call embeddings, is just brilliant. Think of it like a giant map of meaning. On this map, every word is a point, a coordinate. And the cool part is, words with similar meanings, like king and queen, or walking and running, are placed really close to each other. So how in the world does the model learn to make this map? It's actually a really clever trick. You don't teach it directly. Instead, you give it a super simple job, a proxy task. You just tell it, hey, predict the next word in this sentence, and you make it do that billions of times on a huge amount of text. As it does this, it starts to figure out which words show up in similar situations. It learns, oh, king and queen are often surrounded by words like throne, palace, and royal. So it naturally starts grouping them together on its map. It learns the meaning from the context.
Okay, so we've got words turned into numbers, and those numbers capture meaning. Problem solved, right? Well, not quite. This creates a whole new problem. A sentence isn't just a random bag of words. The order is everything, and these embeddings by themselves have no idea about grammar or sequence.
I mean, think about it. The bear ate the fish versus the fish ate the bear. Same exact words, right? Same embeddings. But the meaning is completely different. One is a normal Tuesday for a bear. The other is a horror movie. So how does the model figure out that critical difference? Well, the first big attempt to crack this was something called a recurrent neural network, or an RNN. And the idea was pretty intuitive. It tried to act like a human, reading the sentence one word at a time from left to right. And as it went, it kept a kind of running memory of what it had already seen. And you know what? For its time, this was a huge leap forward for understanding sequence. But, and this is a big but, RNNs had a fatal flaw. They had a terrible memory. I mean, they were incredibly forgetful. As sentences got longer, they just couldn't connect the dots between the beginning and the end. This problem got a name: the challenge of long-range dependencies. Okay, look at a sentence like this. The man who lives in the big blue house on the corner of the street where I grew up, right next to the park with the old oak tree. Okay, you with me? The RNN is reading along word by word, but by the time it finally gets to the end, is happy, it's completely forgotten who we were talking about. The man from way back at the start? Gone. All that crucial context is just lost in the noise. Now, the technical name for this is the vanishing gradient problem, but a much better way to think about it is like that game of telephone or Chinese whispers. You whisper a secret to the first person in a long line. By the time it gets to the very last person, the message is either totally mangled or it's just gone. For an RNN, that learning signal from the first few words gets weaker and weaker as it goes down the line, until it just vanishes. So this memory problem, this vanishing gradient, was a huge roadblock. And it set the stage perfectly for the next massive breakthrough. An idea so elegant, so powerful, it would literally change everything. It was called the attention mechanism. So instead of forcing all that information through that one word at a time bottleneck where the memory fades, attention gives the model a superpower. It gives it a direct connection to every single previous word in the sentence all at the same time.
It's like going from a terrible fading memory to a perfect photographic instant access memory of the whole text. There's a really great analogy for this, the librarian. So imagine the word the model is currently looking at is you. You're the query. You go to the librarian with a question. The librarian then looks at the title of every single book in the library, those are the keys for all the other words, to see which ones are most relevant to your question. And once it finds the best matches, it pulls those specific books off the shelf and gives you the information inside them. That's the value. It's a way of finding and retrieving the most important information from anywhere in the text. So you have this amazing new tool, this attention mechanism, but it needed a new home. It needed a whole new kind of model, an architecture built specifically for it, designed from the ground up to unleash its full power. And that architecture was the transformer. And in 2017, a paper came out with this just unbelievably bold title, Attention is All You Need. It was basically a declaration to the entire field of AI. It said, you know that old way of doing things one word at a time? It's over. Attention was the future. At the absolute core of the transformer is this idea of self-attention, and that's the magic right there. It means that for any given word, it can look at every single other word in the sentence, all at the exact same time to figure out its own meaning. That one word at a time bottleneck that held RNNs back, it was just gone, smashed. And this shift was a total game changer. And not just because the models were better. Because they could process everything at once, in parallel, they became massively faster to train. And that speed, that efficiency, is what suddenly made it possible to train them on truly gigantic amounts of data. Which brings us to the final, and maybe the most important question of all. So you have this incredible new architecture. It understands context better than anything before it, and you can train it at an unbelievable scale. So, what happens when you decide to feed it, well, basically the entire internet? Well, you get what we have today. You get the large language models that are completely changing our world. It all comes back to this. It was never magic. It was just a chain of really, really smart ideas, with each one solving the problems of the one before it. And now, you know the story behind it all.